Okay, so next we will move on to one other improved improvisations on VAE, which is called vector quantized VAE or VQ-VAE. Vector quantized VAE or VQ-VAE. So as far as the families of VAEs are concerned, the VQ-VAE is the current state of the art that is used often in practice. Okay, so what is a vector quantized VAE? So in a vector quantized VAE, in VQ-VAE, the first thing that is done is the latent space is made discrete. Latent space is discrete and vector quantized. Vector quantized using a learnable dictionary. I will explain all this using a learnable dictionary. Okay, the idea is the following, right? In the VAE that we saw so far, the latent space was continuous because it was coming from a normal 0 1 normal distribution with 0 mean and unit variance and so on. But in practice, if you look at the practical data, for instance, images or speech or text, etc., it is intuitive to think of the latent space be having discrete representation, because if you think of speech, okay, a speech signal can be represented using a finite set of phonemes. So phonemes are these abstract linguistic units corresponding to the sounds. For instance, a is a phoneme, e is a phoneme, u is a phoneme, and so on. So every speech utterance or speech signal that you see can be thought of as a combination of different phonemes. So which means that speech signal can be, any given speech signal can be represented using finite set of phonemes. So similarly, one can think of the fundamental units for an image as well. So every image can be represented in terms of, let's say, primitive structures such as lines and circles and different kinds of primary shapes and colors and so on. Okay. Of course, in the case of images, the number of discrete such latent primitives may be large, which is okay. But the idea is that the intuitive idea is that the practically occurring data such as images, speech and text, etc. Text is very obvious to see text as a set of combination of set of discrete tokens. Okay, tokens can be alphabets or they can be combination of alphabets and so on. So every data can be represented better using a discrete set of latent space or symbols, and that is the reason why a VQ-VAE operates the latent space in a discrete sense. Okay. Now, how is this done? So the latent VAE is also VAE, therefore it contains an encoder and a decoder structure. Here in a VQ-VAE, the encoder and decoder are deterministic in the sense that, unlike in a VAE which gives you the samples of Q phi of z, the parameters of Q phi of z1x, in the VQ-VAE we get the samples of Q phi itself, not the parameters. Okay. Now this will take xi as an input, the input data point, and the output of the encoder, this is the encoder, which is the deterministic encoder, which means that it will give a vector, let's say ze of xi. Okay, gives a vector ze of xi, and now we have the decoder. That is the decoder network, and decoder network takes the vector quantized version of ze. I'll tell you what that means. So let's call this p theta, and gives back x cap of I. Okay, this is the reconstructed data point. This is the decoder. Now we have what is called as a latent dictionary. Let us call that as z1, z2, up to Zm. So this is the latent dictionary. Okay, this is a latent dictionary. Now let's say that every Zi in the dictionary is in some k dimensional space. Okay, now suppose there are m latent vectors of k dimensions each, okay, in the dictionary. So there is a latent dictionary, let's call that some L. So L is a set of vectors Z1, Z2 up to Zm. So there are m such vectors. Okay, all of these vectors Zi, they are in some k dimensional space. So we have an m cross k matrix which forms the latent dictionary. Okay, now what happens is ZQi, which is the quantized version of the latent space, is simply Zj star, where J star is that index J equal to 1 through m, that index which would minimize a distance between the output of the encoder and an element of the latent space. Okay, so this process is what is called as vector quantization. Now what's happening here? You have an input data point and the encoder gives some output Ze, which is some vector. Now what we do is we take that vector, okay, take that vector Ze, which is the output of the encoder corresponding to a given data point, and we search in the dictionary, latent dictionary, for that vector which is closest to the output of the encoder. So that would give us that would actually give us one of the elements from the latent dictionary, which we will call as ZQ, which is the quantized version of Xi. So now that quantized version of ZEXI is the one that goes as the input to the decoder. Okay, so now I hope that this is, I mean, the idea of vector quantization is explained properly. So now in practice, what happens is the latent space is designed to be a tensor of latent dictionary vectors. So what do I mean by that? So let's say that my latent space is latent vector is taken to be a matrix of each of this has let's say each, we'll take it as column wise. So each of these columns are one of these vectors. So we have dimensionality of this is k. So we have k rows and p number of columns. Okay, so where each row is a vector from the dictionary L. Okay, so each row will happen to be a vector from that particular dictionary. So your latent vector is made a matrix of p such vectors. So what is done is each row, or rather each column of, so let me call this as Z cap xi, okay, which is the latent vector. So Z cap xi is the output of the encoder, okay, this is given by this particular, each column of C cap of xi, so let E of xi is vector quantized, that's all. Okay. What do I mean by that here? So the ZE, okay, let me call this as Z cap of E, so this is ZQ. So now Z cap of EXI is a matrix that has a p number of vectors, okay, from the latent space. So now this is ZE of xi is in k cross p dimension. So this is nothing but p vectors from the latent dictionary. Okay. So now p here is a hyperparameter depending upon what the application is. Okay. Then what we do is each column of this ZE cap xi is quantized. So that is what is done here. So ZE of xi is a column of the matrix Z cap E of xi. So every column is quantized. Okay, that is how it's done practice. So why should this be done? Is because if you take only single vector as the output of the encoder, that may not be representative enough for data sets like images and so on. Therefore, the in practice, this is made to be of a dimension k cross p, where each of the columns of this particular matrix is one vector from the latent dictionary, which is vector quantized. Okay, so that is the idea. Now, this is the design of a VQ-VAE. How do we train a VQ-VAE? It is trained very similar to that of a VAE with the elbow cast. So let's look at training a VQ-VAE. How to train a VQ-VAE? Let us write down the objective. The objective is say j theta of q for the VQ-VAE is, of course, we have the reconstruction task, which is x minus output of the decoder, and this of course takes ZQ as the input, ZQ cap as the input, plus we simply have the regularization cost, where we need the output of the encoder to match the quantized version for each of the dimensions. This is the cost, that's all. Okay. Now, unlike in a VAE, this is the usual VAE task, right? VAE objective. Unlike the VAE, here we also learn, in addition to the encoder and decoder parameters, the encoder and decoder parameters, the latent dictionary is also learned. Now, what do you mean by that? So we do a gradient descent on each of the elements of the latent dictionary via this. So we will take this and simply find the minimum, the gradients with respect to Zj, okay, of this particular cost, which is j theta of q. Okay, right. So please note that here the gradients are with respect to the elements of the latent dictionary itself. So we are learning the latent dictionary as well. So we are not only learning the parameters of the encoder and the decoder, but we are also learning the latent dictionary itself by taking the gradients of the elements of the latent dictionary with respect to elbow, right? So this is how a VQ-VAE is trained. Okay, so now once it is trained, how do we do inference in a VQ-VAE? Inference in a VQ-VAE is done as follows. So let us first look at the posterior inference or embedding extraction. I think that is easier. We'll go to generation in a while. So the first thing is the embedding extraction. Or what is called as the posterior inference. So as usual, the posterior inference or embedding extraction is done via the encoding network. We take the trained encoding network in a VQ-VAE. So take a trained encoder in the VQ-VAE. Take X test, which is for which we need the encoding. So this is Q P star, and what we get here is the output of the encoder, which we'll call XZ test, or rather X cap Z test. Then what we do is the embedding Z cap Q test, which is the embedding, is simply taken as the vector quantized version of, which is so argmin j equal to 1 through m to solve this optimization problem, which is ZE cap X test minus the one in the dictionaries, right? So just take the vector quantized version of the output of the encoder from the dictionary, do it for each of the columns. So as we said, no, this is in some R k cross p, right? So this will also be in R k cross p, but we vector quantize each of the columns of this particular matrix, and thus that would be our embedding for given X test. Okay. Now this is easy. How do we do generation or sampling in VQ-VAE? That's a non-trivial thing. Sampling in VQ-VAE. The problem with sampling in a VQ-VAE is that unlike in a VAE where we know what the distribution of Q-phi of Z given X is, here we are not imposing any particular distribution on Q-phi of Z given X, which means that sampling from that distribution is not trivial. So here what are we getting? We are getting the decoder is taking ZQ of X, okay, and this is giving you the sample X cap. Okay, so now to be able to generate a data point, let me write that down. To be able to sample from the decoder of VQ-VAE, we need to first sample from the distribution of ZQ, right? So because only if we know how to sample from the distribution of ZQ, that we can take that as an input and give it to the decoder of the VQ-VAE and generate. But now we don't know what the distribution of ZQ is, unlike in the case of a VQ-VAE, a VNI VAE, where the distribution of the latent space was known and it was made to be equal to normal 0,1 by the KL term. Here we don't know that, right? So now how do we solve this problem? Is typically what is done is the following. So to first learn to sample from the distribution of ZQ, okay, generative model is learned model is fit to samples of ZQ. So what does this mean? This means that you take all the input data points, pass it through the encoder of the trained VAE, trained VQ-VAE, collect all ZQs. So on the collection of all those ZQs, treat it as a data set and learn another generative model on top of it. So this can be a GMM on the samples from the output of the encoder. Output of encoder corresponding to all input data points. All input data points, right? So given a set of data set that we have, right, a lot of input data points, pass all of them through the encoder. So you will get the corresponding latent representations. You fit a GMM on top of it, which means that you learn another generative model on top of it. So once you do this, so this will enable us to sample from the distribution of ZQ, right? So then sample from the learned distribution of ZQ and use it as the input to the decoder. That's all. So this is a little convolutive and cumbersome to sample from a VQ-VAE. So what did we do? I'll just repeat. Now to sample from the decoder of the VQ-VAE, we need to know the distribution of the output of the encoder. Okay, that goes as an input to the decoder. Unlike in a VAE, we don't know what the distribution is. So what is done? Just learn another generative model, okay, meta generative model on top of the output of the encoder. That would tell us that will give us a method to sample from the distribution of the latent space of the VQ-VAE. Using that generative model, get new points from the distribution of the latent space and give that as an input to the decoder of the VQ-VAE to sample. Okay. Because of the cumbersome nature of this, VQ-VAE is not typically used as a generative model. It is generally used as a feature extractor. In fact, in a lot of state-of-the-art models for image generation, the latent space of VQ-VAE is used as a starting point. In fact, a model called stable diffusion, which is state-of-the-art for diffusion models for image generation, uses the latent space of a learned VQ-VAE as the starting point. Okay, so which is the posterior inference. So basically, given a data set of images, take a VQ-VAE, take the encoder of the trained VQ-VAE, pass all the input data points, image data points, and represent them with the latent spaces of the VQ-VAE, latent vectors of the VQ-VAE. Okay, and that is used for further processing to build a diffusion model, as we will see later. Okay, so this takes us to the end of discussions on variational autoencoders, which is the first of the models from the family of latent variable models that we will be seeing in this course. Now, next we will be looking at another state-of-the-art generative models called the denoising diffusion probabilistic models, or diffusion models in short. We will be looking at diffusion models, which happens to be a special case of family of VAEs called hierarchical VAEs. So we will connect that to the hierarchical VAEs. So diffusion models forms the basis for most of the generative models on image space that are present in the market currently, state-of-the-art models. We will be looking at diffusion models as the next family of models. Thank you.